Welcome to a terrific Thursday, everyone. Thank you for showing up for your learning. And I am excited to take you on a tour of exponential growth and exponential decay. So again, we will go through these examples as speedily as we can. We spent a lot of time with transformations this morning. I don't think you can spend enough time with transformations. Tomorrow we'll have some time to work on our projects, and I'm very much excited to play test some of your ideas. So I will be doing that tomorrow as well. All right. Exponential growth describes a situation where you have things that grow over time, and their growth looks like this curve here. This curve, called the exponential growth curve, and we've all been given a big lesson in this during the pandemic. We have um, COVID cases that tend to grow exponentially, and we'll take a look at the math behind that type of outbreak science with this idea of exponential growth. If you can reduce the transmission rate of something like a virus, then you can turn that exponential growth into exponential decay. And you can have the cases start falling off and approach zero again if you can reduce the number of people that the average infected person distributes the virus to. Now, I don't want to spend much more time talking about COVID cases, but I do want you to understand that this math does follow that. So we will talk about things like viral videos or populations, or money will also grow exponentially or decrease exponentially if we look at inflation. So this type of function is known as exponential growth. Let's keep going. So here is an expression. This is the equation that we will use to talk about exponential growth. This is a function. Amount is a function of time. So time is usually the independent variable that we will have measured along the x-axis. And so amount is the thing that we'll measure on the y-axis. So this is a function, and we need an initial value. And we use the letter a. It's the same letter that we had in our transformations. It's also the stretch factor of the function, mathematically speaking. But practically speaking, when we're looking at word problems, your initial value is actually your A. So if you wanted to know, this video is so cool, and everyone who watches it will send it to two of their friends, let's say, okay? And the initial audience for this video was this class, say 30 people. You would use A as your initial value of 30 people. And then B would be your growth factor. Every person that sees it sends it to two more people. So every generation of shares is going to be twice as big as the last generation of shares. So we would have a growth factor here of 1 plus the rate, right? So the growth there would be, it gets shared to two people. So it's growing by double. So if we wanted to know generation after generation, how many people have seen that, we could use the number 2 there, and it will tell us the size of successive generations, not the cumulative number of people that have seen it. And then T we would have for time. It takes time to watch the video and then share it, so that would be, we would be measuring time and generations of shares of the video. Action. This one we'll look at next. This one we'll look at. We're not so much following along because that should fall. So, growth factor here is the base of the exponent. That's the number that's being squared or being cubed, or that's being raised to the power t. And we can construct that by the expression 1 plus r. So people like money. If you have, what's about the percentage of interest that you're getting in your savings account, for example? Does anyone know? Sorry? 1. Yeah, it's like 1%, right? So if we were to express the money that you have in your bank account, let's say we want to know a function, a of t is the amount of money you're going to have in your bank account for different times t. And you have a good $100 in there right now. That's the initial value. It's $100. And then we're going to multiply that by 1 plus the interest as a percent. But we have to express that percent as a decimal. So you told me that you are getting 1% interest. So that would look like this, 1.01. 1 plus the interest. Okay? And then we could raise that to the power t, and this would be an expression that would tell me after X number of years, after T number of years, how much money will you have in your bank account. So you will see after T is 1, you would earn $1 of interest. This would be $101. Not very exciting, right? It's hard to get excited about a 1% increase unless you have about 1,000 years, and then it's very exciting. Okay, let's keep going. But that would be just an example of how I could set up one of these problems. I want to understand initial value, rate. I build the rate by 1 plus the rate as a decimal. Okay, so I take the percent, I convert it to a decimal, and I use that as rate. And then I have t as my time. So if I have equations like this, let's just unpack these. This one could be describing someone that has $400 in some kind of savings, but they're getting 12% interest. That's actually pretty exciting. It's not going to be exciting after a couple of years, but after 10 years, it's going to more than double. I think that triples in 10 years. Anyway, the initial value here is what? You got to shout at me. You got to go fast so that you get more time to work on your own. 400, good. So this is a 400 initial value. It has what growth factor? 1.12. Yeah, 1.12. What's the percentage increase year after year? 12%. Very good. Now over here, I have 243. This could be a number of views of a video. That's weird. I did the 3 first. 243. That could be how many people see the video in the first generation. What's the growth factor generation after generation? 1.6. What's the percentage increase? 60%, not 6%. 60, because this is 1.60. Okay. So that is unpacking these types of equations and seeing this is my A, this is my B, my growth value, and the growth value is 1 plus the percentage increase. So that's I'm glad to see people can quickly convert decimals to percents here. That's good. Here's an example type question. We start with 100 frogs. We increase them at an annual rate of 22%. How many frogs will there be in 5 years? So we set this up. A of t. Amount of frogs is a function of time t. And that's equal to, I put my initial value first, 100. I like to put my growth factor in a bracket. What's my growth factor here? What's my B? 1.22 is the right answer. So exciting. The knowledge is just flooding out of you. And then I raise that to the power t. I want to know how many frogs there are in 5 years. So now I evaluate. A at 5 is equal to, someone has a calculator. Someone's going to shout the answer at me. I should bring fun-sized chocolate bars to lob at you parabolically. 270.3. Can I have 0.3 frogs? No? So it's about this many. Yeah, right. That's very good. Yeah, and I need a blender. So here, 270.3. I can actually keep these decimals. Why? Even though I can't have 0.3 frogs.
For accuracy.
Well, this is just like a general type of guess. Okay, it's going to generally follow this 22% increase, but frogs and natural phenomenon are not going to follow our math very precisely. It's going to be in and around that. You know, there's going to be some variation of the actual data to the mathematical prediction. The mathematics predicts 270 frogs and maybe a little bit higher than that. So that's fine. Example, solving T. The population of a city grows at a rate of 5% per year. The population in 2003 was 400,000. In what year can we predict the population to reach 1 million? Okay, so here we go. This is how we can solve this type of question. A is a function of t, is a function of time. We want to set up our equation. So we have in 2003, so we can say let 2003 equal year 0. Okay, so that's year 0. After 1 year, 2004, we want to input a 1 and multiply our growth factor by itself that many times. One growth factor in 1 year. So that's why we need to let 2003 be year 0. So we know that this is 400,000 multiplied by, what says, oh yeah, weird. 400,000 multiplied by, what's my growth factor? 1.05. Notice that 1.5 means that if I multiply this by 1.5, I'd get 600,000. The population would be growing by 200,000 per year if I make this decimal error. That's a huge mistake if I put 1.5. 1.05 is correct. That's 5% as a decimal. Notice that that's an easy mistake to make, and you don't want to make it because it throws your numbers way off. Way off. That's a big difference. So here we go. Now I say, how long will it take for it to reach this?
30 years.
30 years? How'd you do that, Desmos?
No, I did the math in my head.
You did?
Yes.
Is that right?
Yeah, I'm pretty sure.
Cool. Okay, let's see. Here's how I would do it. The spoiler alert, I'd use Desmos. Okay, so now I know that I want to find out when it's going to be that many people. And so I put that in on the amount side. This is how many years will it take for it to reach that? So it's going to reach that at some time. If it keeps growing, that should make sense. And then I have 1.05 times t. Okay, now inverse operations. I can divide both sides by 400,000. Okay. Okay. 1 million divided by 400,000. What is that? It's 10 over 4. It's 5 over 2. So this is 5 over 2 is equal to 1.05 raised to some power t. Now what do I do? Now what can I do? Use decimals. So I can also just go from here and plot the whole thing in decimals. And this is what that looks like. At this level, you can use decimals for these ones. So here, what I will plot is my A of t. I'm just going to plot that as y is equal to 400,000. Is that 400,000? No, it's 4 million. There's 400,000 multiplied by 1.05 raised to the power x. Oh, I can't see anything. Oh, that's because I really need to change my scale here. I really need to zoom out because that's a little big. So I definitely want to see x values of, like, Brody says it's 30 and he did it in his head.
Well, I got it wrong because
About 20.
it's like
Okay.
because like after the first year you get 420,000 and then you have to do the rate off of that number. So it's like
Okay. Here is, I'm just going to show 1.5 million on the y-axis. There we go. So I've changed my scale so I can see the business area that I'm interested in. And I want to know, when does that reach a million? There it is, it's right there. It's a little shy of 20. So actually, Brody, your guess of 30 is not that bad. It's pretty good. Shows good instincts.
I use the calculator.
Oh yeah, did you use logs?
The table function.
Oh, the table function, eh? Okay, cool.
About 19.
Yeah, it's about 18.88. So there we go. Here, if I want to know exactly when it crosses a million, I can just graph the line y equals a million. That's the line y equals 10 million. So here we go. Y equals there. And there, find the intersection point. There it is, 18.78. 18.78. So that's your answer. In 18.78 years, it will reach that size. So just use Desmos. You can solve these. You need logarithms. We don't do that at this level. That's going to be grade 12. Actually, in grade 12 college or in grade 12 university, you'll learn to solve those types of problems where your variable is the exponent. So according to Desmos, t equals 18.78. So I'm just going to say 18.8 approximately. That's an approximate answer anyway in Desmos. So 18.8 is good. Therefore, in what year? In what year will that happen? Someone tell me. Hello, welcome. Thank you very much for your help and for nourishing us.
2021.
Yeah, in 2021 and like what is that? 10 months? Like 9 and a bit months. Yeah. So therefore in 2021. Oh, right about now actually. Right about now in 2021, maybe mid-October or so, the population reaches 1 million.
I don't think it's very accurate though, because of all the stuff that's happened with COVID-19 and people moving out of cities and all that.
Oh yeah, these are predictive models. So we want to remember these are predictive models and that they're based on past behavior. Past behavior is a good prediction of future behavior, but since our society has gone through several cataclysms recently, you know, take it with a grain of whatever grains you want to count. Dave.
How do you do that algebraically again?
Oh, algebraically, you need logarithms.
Pardon me?
You need logarithms.
Oh, you can?
You can. We don't in grade 11. You will next year. At this point, I want you to know you always have a road to a solution available to you if your Desmos chops are good. I remember being a supply teacher in a grade 12 class, a math class, when they were reviewing for their exams, and it was like my first assignment in Simcoe County, and I went there, and someone said, "Excuse me, sir, but can you solve this problem?" I said, "Oh, I forget how to do that algebraically, but here, Desmos is really quick, so it gives you an answer." She was happy, but I don't think that helped her for her test. Okay, now let's take a look at exponential decay. Exponential decay are situations that look like this. Okay? This is where something is shrinking at a constant multiplicative rate over time, and these are called exponential decay. Okay? These are decreasing rapidly in the beginning and then slowly over time. And the multiplicative rate is now between 0 and 1. The only difference between an exponential growth and exponential decay is this b number here in growth was 1 plus r. In decay, we're going to have this number be 1 minus r, where the rate is the percentage decrease as a decimal. So this number is going to be between 0 and 1. People like told me your favorite numbers at the beginning of the year, and they were all integers and they were all bigger than 1, or they were integers. But the range of numbers between 0 and 1 is equally interesting as all of the other numbers. There's like 1/10, 1/100th. These are all very different numbers and they're very interesting, and we see the power of these numbers between 0 and 1 and their importance inside something like exponential decay. So here it's the same formula, the same place. We have initial value. We have a b value here, which is our growth factor. This time the growth factor is going to be less than 1, but bigger than 0. And then time is t. Okay. So if we look at these examples, we have here, what's my initial value with this thing that's going to exponentially decline? This has an initial value of 20. And what's this growth factor be? With this one, what's the growth factor? 0.87. And so what's the percentage decrease over time with this one? 87% is how much of the thing you will have after 1 year. So how much percent did it decrease from 100%?
23%.
Forgot to carry a 1. Liam? 13%. 13% decrease for this one. So this is decay. If I graph this in Desmos, let's take a look at what we get. So I'm going to get just a fresh Desmos window. 20 times 0.87 to the x. Fresh Desmos window. We're going to have 20 times 0.87 raised to the power x. And here it is. This is what this will look like. At its initial value, 20. and then it lowers by 13% every year until at 10 years, there's well less than half of the stuff left. There's about a quarter left at 10 years. And then it goes down by 20 years. There's only like a little bit more than a 20th of what we started with. And then it'll never be zero. There'll always be something there, but it's getting smaller and smaller and smaller as we go forward in the years. So that gives you an idea of what these graphs will look like when we have exponential decay. Now here's a funky thing that I want to show you. I can create this with an exponential growth of 1.3, but then I will just have a negative x value here. Oh, this is raised to the power negative x. Yes, that's pretty close. It should be a little different because that's not quite right. So I can tune that a little bit to make that like 1.1 there, 1.5 or so. Yeah, there, it's about there. It's a negative k. I'll talk about that later. So we'll have a cleaner algebraic example to show you. So here, 54 times 1.05 raised to the power t. What's my initial value here?
54.
Yeah, 54. What's my growth factor? 1.05. And what's the percentage increase or decrease? 5%. Is that giving me growth or decay? Growth. Good. So I recognize this number is bigger than 1. It's going to grow. This number is smaller than 1. It's going to get smaller. It's going to shrink. It's going to decay. So in 2005, there were 85 rabbits in Central Park, but the population is decreasing by 12% each year. So first, we want to find out an equation that's going to model this. The amount of rabbits is going to be a function of time. And what will I use as my initial value? 85. Thank you for all shouting it out at the same time.
85.
85 rabbits. And what do I put in here for my growth factor?
1.12.
1.12. The population decreased by 12% each year.
Oh, 0.88.
Good. 0.88. And I raise that to the power t. So now I want to know how many rabbits were in Central Park at 2015. But this here is my year 0. This is 0, 2005. So what should I put in for t to calculate in 2015? 10. I take my year 0. I have 2015, subtract my year 0, which is 2005, and that will give me 10. So I want to calculate a at 10. That will tell me after 10 years of decay, how many rabbits are left. 85, and this is going to be a little creepy because we are going to have fractional rabbits here to the 10. Someone has a calculator. Someone will shout this answer out at me, I'm sure, while I sip coffee.
23.67.
23.67, you cruel person. Why couldn't you have rounded that to 24 rabbits? Anyway, there will be about 24 rabbits in the year 2015. Suraj?
For the original equation, why can't you have it as t minus 2005?
Oh, yeah, you could. Yeah. And then that's you're like vertically translating. It depends on what section of the graph you want to look at. If you wanted to know how many rabbits were in Central Park in the year 0, in the year of like Christ's birth or what have you, that's actually 4 years after his birth apparently. But anyway, that would give you some like billion, cajillion, bamillion rabbits. So there's actually no significance to all that, so I would exclude that from the domain anyway. And if I'm excluding it from the domain, why not start my graph there? Unless I have move the axis over and show it. It's up to you. It's kind of an aesthetic choice at that point. I like using t values that are like, I don't have to do math when I do my t value, or I like to do my math and then put it into my t value. There will be about 24 rabbits. Okay. A city finds that its residents are moving to the suburbs. The population is declining at a rate of 4% per year. given that the original population was a million, how long will it take for the population to decline to half its initial amount? So in this one, I don't actually need to set up the whole equation in the same way, but I might as well. So will have an A of t is equal to original population, 1 million, multiplied by, it's not 1, 0.96, Siraj says. Siraj gets his growth factor of 0.96 by taking a look at a decline of 4% per year. So that's 1 minus 0.04 gives me 0.96. Okay? And then I raise that to the power t. And I want to know how long will it take for the population to reach half its initial amount. Actually, the population and its half are going to cancel out because I'm going to be solving this equation. 500,000 is equal to 1,000 multiplied by the growth factor or the decay factor to some power t. Okay? And what I'm going to now do is divide both sides by a million and then just have 1/2 on the other side. So that's 500,000 divided by a million. That's going to give me 1/2 is equal to the growth factor raised to some power t. I could have just set this up right from this. How long will it take for the population to decline to half its initial amount? Okay. If there were 10,000 people, it would be the same question. It would be the same answer, sorry. 10,000 would decline to 5,000 with this growth factor at the same speed that 1 million would decline to 500,000. So I could have just set this up right away based on what the problem was telling me. And then this is something that I can plug into Desmos and I can solve. So if I say, here, go to a fresh Desmos tab. Okay, and I'll use this one. If I know that y is equal to, and I could put in a million here, but I also showed you that I don't really need to. 0.96 raised to the power x. And then I want to know where does that hit a half? So y is equal to 0.5. Okay? And then there it is right there. Let's zoom in so we can see it. So here's the effect of our growth factor. It's not declining very quickly, as you can see. It looks quite a lot like a line, but it is not a line. If I zoom way out, you'll see it's still this exponential function. The population 100 years ago would have been millions and billions and trillions. That's why going backwards with this data is kind of meaningless. We don't do that. But it's still behaving like an exponential. Oops. I need to get over here, and I need to zoom in. Okay, there we go. So this is our population, and it declines to half its population at the intersection here. It's around 17. 17, 1.5. 16.98, 0.5. So that's where it's in the year 17 that it will do that. Okay, so, I'm over here. So therefore, investigating in Desmos reveals that t equals about 17. It's approximate. And how long will it take? So it will take 17 years. Okay, Joan told us it was break, and it is break time. Oh, yeah, so thank you for tuning in for your learning, and I hope that your math practice is very fruitful today.